So in the past lessons, we did vertex form, where we were able to pull out the vertex from that quadratic function. Now we are looking at standard form. Before we continue, I wanted to show you example number 1, a table of values. I want to show you how to identify if something is quadratic. So let's look at this first example here. This first example, if you look at the x's, they're increasing by 1 each time. If you look at the y's, they are actually increasing by 2 each time, because to go from -4 to -2, you have to add 2. So that's going to happen in each case. This is called a linear function. So that's what you did in 10C. So that is when the first change that you look at for y is constant. So if you see a constant change between the y values, that is a linear function. So that is not quadratic. Let's look at the next one here. Here, again, we have that we're increasing by 1. From 1 to -4, we are subtracting 5 to get from one number to the next number. From -4 to get to a -11, you would have to subtract 7. From -11 to -20, you would subtract 9. And from -20 to -31, you would have to subtract 11. So as you can see, this is not a constant change, so it is not linear. Not linear. But let's look at the next change. How do we get from -5 to -7? Well, I would have to subtract 2. To go from -7 to -9, I would also have to subtract 2. And from -9 to -11, I would have to subtract 2. This second change, so this would be a degree of 2. This is when it becomes constant. So a degree of 2 is when x is squared, versus a linear is when x is to the power of 1. So as you can see, this one is quadratic, because the second change of y is constant. What we want to do is be able to go from factored form into standard form. Standard form looks like this. In 10C, you should have learned that to put two brackets together, you can do something called FOIL. That's when you multiply your first, your outside, inside, and last terms together. So that's going to give you 3x squared plus 6x minus 4x minus 8. And we always want to combine like terms together, so the middles are going to combine, giving you positive 2x, and we have a minus 8 as our constant. This is our standard form. In our next case, this is vertex form. I want to show you how to go from vertex form to standard form. So step 1, whenever we see something squared, we would write it out twice. So x minus 3 is squared, so we wrote it out twice, and we're actually going to do FOIL with those two brackets. So in BEDMAS, we do brackets first. So we're going to go -2, and in brackets, we're going to multiply the first terms together, which is x squared, the outside terms, the inside terms, and then the last terms gives us plus 9. And we still have this plus 4 sitting outside. Now we're going to distribute that 2 to everything. So that's going to give us -2x squared, positive 6x, positive 6x, and minus 18, which is adding with 4. So our standard form would be y equals -2x squared, positive 12x, and then minus 18 plus 4 would be minus 14. So there's standard form. So we always have the highest degree first, which is 2. Then we have to the power of 1 next, and then our constant comes afterwards, the very last term. For each quadratic function in example number 3, we're going to identify all these key characteristics. So these are called key characteristics. So we want to be able to identify these for all quadratic functions. So whether they're in vertex form or standard form. So as you can see, we already have our graph given. So we have a graph given, so we're going to use the picture to help us. So the direction of the opening, in this case, this A is upwards. Another reason we know that is because the value in front of x squared is positive, even if you don't see it. In our next case, we see that there's a negative sign, so that one is downward. The coordinates of the vertex are always either the lowest point or highest point on the parabola. In this case, A, we have the lowest point should be labeled as -3 and -4. So -3 and -4. B, our vertex looks like it's at 1 and 4. Now, this one is right on the graph, so that's why I'm using the graph. It looks exact. Now, I would not guess or approximate the value. I would always use my graphing calculator, which I will show you in the next example how to find these answers with the graphing calculator. For A, it's asking if it's a max or a min value. When it's a upward facing parabola, it's going to have a minimum value. And in our case, our minimum value is when y equals -4. It's always going to be the same as our q value in our vertex. In our downward facing parabola, it's a maximum. And that's going to occur when y equals +4. Our axis of symmetry is always the same as our p-value, which in our case for A is -3, and for B it's x equals 1. So the x-coordinate of your vertex. The x-intercept is where the graph touches the x-axis. So in our first graph, A, we have the x-intercept is equal to -5 and -1. In B, we have the x-intercept is -1 and +3. Our y-intercept is when the graph is touching the y-axis. So our y-intercept in this case, it might be hard to tell, but a little trick is it's always going to be the same as your constant in your standard form. So there's your y-intercept. So in the y-intercept for the first graph would be 5, and the y-intercept for B would be 3. The domain x such that x is an element of real numbers is true because this graph is extending forever left and right. That means all x values are allowed. And then y such that it should be still domain. X such that x is an element of real numbers as well. So they both extend forever left and right, even if it's upward or downward. So there's no situation attached for it, so that's why I can go XER for both. For the range, I would say y such that y is greater than or equal to -4 YER. And y such that, so whenever you see that it's an upward facing graph, you should always have it being y is greater than or equal to. And then you would use the minimum value that we found above for what we're saying it's greater than. In B, we should say that since it's a downward facing parabola, it should be y is less than or equal to. What we're saying is that the graph is below this value, so less than or equal to 4 YER. Okay, so that's how we look at the graph and find out the key characteristics. Example number 4. A diver jumps from a 3-meter springboard with an initial vertical velocity of 6.8 meters per second. Her height h in meters above the water t seconds after leaving the diving board can be modeled by the function h of t -4.9 t squared plus 6.8 t plus 3. The only thing we can do right now, just by looking at the equation, is the y-intercept. The y-intercept is always the constant in standard form, and that's going to be equal to 3. And if you look at the situation, that matches how high the diving board is off the water. So that's what the y-intercept represents. It is the height of the diving board. And it's also going to be called your initial height. What was the height that they were initially at? So in this case, it's 3 meters. Now, the other information is not really clear from just looking at the equation. So from this point on, we're going to go to our graphing calculator, and I'm going to show you how to find all the main features you need to be able to answer the following questions. Like, we're going to need that maximum height and when it reaches it. So that's another name for, in C, the vertex. So we will have to find that with our graphing calculator. So we're going to go to our graphing calculator. We're going to go to y equals. We're going to clear whatever's there in y equals. And you're going to enter the equation exactly how you see it. But instead of h of t, we're going to replace it with y, which you see already given. And your t is going to represent the letter x. It's going to be replaced with letter x because we don't have those other letters to use. So we want to use negative 4.9. Instead of t squared, we're going to say x squared plus 6.8 times x plus 3. Now, our next thing that we do is we go to the window and we set it to the standard window. So that would be where your x minimum is negative 10, your x max is positive 10, your scale is 1, your y minimum is negative 10, your y maximum is positive 10, and your scale is 1. So this is called the standard window. So I usually start with this and then I adjust depending on the situation. So let's graph it and see if we can see a nice parabola shape. So we're going to press graph. This is good. So as you can see, we have the diving board. She's jumping off the diving board at the y-intercept value, and then she's landing in the water at the point that is called your x-intercept. So what I want to find is the vertex. If it's a downward facing parabola, we're going to have to go to second, which on my calculator is called shift. So I'm going to do second trace on your calculator. You're going to go to, since it's a downward facing parabola, that's called a maximum. You're going to press number 4, maximum. And you're going to move your cursor left or right until you see it. So you're going to keep moving it either left or right until you locate it. Now, this is approximately where our vertex is, but the calculator doesn't know how to get that. It wants you to restrict and give me an approximation of what values are around it. So it's going to say, what is the left bound? Well, the left bound is, what is the left side of that vertex? So left side would be anywhere here. So anywhere here is your left bound, the left of your vertex. So I'll press enter for my left bound. When it says right bound, you're going to go to the other side of that vertex. So the right bound would be anywhere along here. It can be really close, but I like to kind of spread it farther around so I know that for sure I'm on that right side of that axis of symmetry. Then you can press enter, and for you guys, you're going to have to press enter again. These are the coordinates of my vertex. So 0.695 and 5.359. So let's write that down. So we know that the person is going to reach a maximum height when h is equal to 5.359 meters. It doesn't tell us what to round to, so I just have to the nearest thousand, 3 decimal places. And when they reach that, that's going to occur when time is equal to 0. If I go back, I just want to remember what I put there. It was 0.695. And we're going to say seconds. Okay, so always include the units. So right now we have a few things that are important. We know that the springboard is 3 meters high, and we already know the maximum. So we can start plotting those points, and then the more information we get, the better our drawing is going to be. So this is going to be actually labeled as letter T, because your x coordinate is time and your y coordinate is height. So use the letters that they give you in the actual question. That's a really important thing that I want you guys to remember, is use the variables that they have. Now time is going to go up by seconds, and over here height is going to go up by meters. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So I already know that the y-intercept occurs at 3. So I'm going to plot that. And I know that the maximum height occurs at 0.695 and 5.359. So I'm just going to plot a point approximately where I think that is, approximately there. And the next question is, how long does it take before the diver hits the water? That's another name for the x-intercept. So we're going to go to our graphing calculator again, and we're going to go shift trace, or second trace for you guys. You're going to go to number 2, which is another name for your x-intercept. You're going to press enter, and you're going to move your cursor either left or right until you locate it. Now there's 2 x-intercepts. This is an x-intercept right here where the graph touches the x-axis. So there's one, I just can't get really close to it. And then there's another one approximately there on the x-axis. Now, I don't care about this left one. The reason being, remember, our x-axis represents time. Time cannot be negative. So even if I did find it, it would not be helpful. So I'm going to ignore that left x-intercept, and I only actually care about finding the right one. So if I move my cursor either left or right, I'm going to get as close to the x-axis as I can. They're asking again for the left bound. So if you guys watch my left bound, you see how my value for y is positive? So anywhere my y value is positive, in this case, that means that your left bound has to be positive as well. So as I move more left, I'm more positive. So anywhere to the left bound, you have to have a positive y. So I'm going to press enter. Now, from that x-intercept, I want to move my cursor to the right bound, meaning to the right side of it. And you'll notice that as I move more right, my value is negative. So anytime you see the y value becoming negative, that is your right bound in this particular case. So you'll see that it changes depending on which side of the x-intercept you're looking at. So in this case, my left bound was positive y, my right bound was negative y. Press enter anywhere that you see y is negative. Enter, and for you guys, you're going to have to press enter again whenever they say the word guess. So in my case, I have a 0, which is an x-intercept at 1.74, and the y-coordinate is 0. So 1.74. So that's how long it will take for the diver to reach the water, 1.74 seconds. So we will actually call this our t-intercept for it to match our letters. And now we can plot that. So we know that the diver is going to touch approximately here along the x-axis, and then we're going to draw our parabola. Now I'm not going to include arrows. The reason being is I don't want my height to be negative. Height can't be negative, so I'm not going to go below the x-axis. And my graph will not exist here either, or here, because time is negative. So that's going to be important for my domain. The domain is not going to be XER anymore. It's going to be X such that you're going to put X in the middle, and you're going to say the smallest time. And to be actually more correct, I'm going to use the letter T. So instead of X, remember, I'm going to use the letter T. So T has to be greater than or equal to 0, because that's the smallest time I'm allowed. Time goes from 0 up to where he or she hits the water. It's a she. So it's going to be 1.74 seconds. And then you would say TER because it can be anything in between those values. So that would be my correct domain. Range, you would say H such that H in between would go from 0. So you can be at 0 height, meaning where he touches the water or she, and goes up to the highest point, which we already found was the max. The max we already determined above was 5.359. So then we would say HER, and we're going to use that information. So far we have the domain, the range. Now, since it's a real life scenario, we don't have that XER kind of case, and we don't just say that the graph is greater than or less than a certain value. We actually have to have a minimum to a maximum for both. The last question is, what is the height of the diver 0.6 seconds after leaving the board? We can do this algebraically by substituting 0.6 into t above into the equation. Or we can go into our graphing calculator and do this as well. So I'm going to go to my graphing calculator. I'm going to go, for you guys, a quick way to do this is you can press trace, and then you can enter 0.6 and then press enter. So trace 0.6, enter. That will give you the Y height of when the diver is 0.6 seconds after leaving the board. In this calculator, another method that I can do is I can press second trace number 1. I can enter 0.6 and enter that value, and now the corresponding Y value that you guys see, 5.316, that's my answer. So the buttons I want you guys to press, the easiest way to do it is you go trace, you would go x equals 0.6, and then you'd press enter, and you should find that you get the same answer as me for Y, which is 5.316 meters. And that's example number 4. Example number 5, again, they're giving us an equation, but they're telling us that this object is fired at an upward speed of 60 meters per second. Again, we have time and height, which is meters. So we have to make sure that our numbers, our values make sense. So we're going to have to identify a few features here before we graph it, of course. It makes it way easier. But I'm going to start by going to my graphing calculator again and putting this in. So I can use the first part because it's actually the same. And then I'm going to add 60x plus 1.85. I'm going to graph this. Now, if you use the standard window, do you guys see that you don't see a parabola shape? The reason being is our graph is way bigger than just the standard window. So what I'm missing is I don't see two x-intercepts because I only see it touching once. And since there is a negative, I'm going to go back and just point that out. Since we have a negative in front, that means it's downward facing. So we're missing that maximum value on our parabola. So what you're going to do is you're going to adjust it. Well, I know I can't see the other x-intercept, so instead of going from up to 10, let's go to 15 and see if we can see it. Well, that's good. So now we can see both x-intercepts, which is important. The next thing we don't see is we don't see that maximum. So our graph is not going high enough, so that's when you go to your Y max. Instead of going to 10, let's go up to 20 and see if that's enough. Nope, not enough. So let's go up to 100 now. Graph it, still not enough. So this is a little bit of trial and error that you're doing to adjust it, to learn how to play around with these numbers. So once I doubled it to 200, now I could see that nice parabola shape. So it does take practice. The more practice you get, the more you'll be able to find your graph. So it can be difficult sometimes. This is what you need to practice, is changing your window to adjust it to fit the situation. So what they want us to answer is the intercepts, the vertex, the domain, and the range. So Let's do the intercepts since we're at it. So let's go to second trace, number 2. You can move your cursor left or right until you get as close as possible to that x-intercept. So in this case, the left bound, when your y value is negative, that is left bound, because as you move more left, you'll see that the graph becomes more negative, a bigger negative value. So you're going to press enter as long as y is negative, and then you're going to, when y becomes positive, so watch your y value, when it becomes positive, that's when you know you're in your right bound. So press enter, and for you guys, you're going to have to press enter again. Now you can see that the 0 is negative. Just like in the previous case, I'm not going to include this because time is not allowed to be negative. So I'm going to ignore this x-intercept, and I'm going to press second trace, and I'm going to go to number 2, and I'm going to move it to the other one. So you're going to have to move your cursor right until you get to the other x-intercept as close as possible. Now again, I'm going to move left with my cursor, and you're going to notice that the y value is more positive. So when you're left bound, you're positive. When you're right bound, you should have a y that is negative, which as you can see, it's negative 9.11. Y is negative. Press enter and then enter again for you guys. So I know the graph is going to touch at 12.276. So let's write that down. 12.276. The y-intercept, I don't have to actually find it because I know that in standard form, this is my y-intercept. So we might as well use that. So the y-intercept, whenever they're asking for intercepts, they want the x and the y-intercept. So we have to write 1.85 as well. Now, remember our graph is quite large. It's going up to 200. So I'm going to change my scale to go up by 40s. 40, 80, 120, 160, and 200. And for my x's, I'm going to go up by, let's go by 2's, because that would be enough to fit my x-intercept in. So 2, 4, 6, 8, 10, 12, 14. So this is going to be my t time, and my y-coordinate is my height. So we already know that we have this y-intercept of 1.85, so I'm going to draw this really close to the x-axis, as close as I can. And my x-intercept I already know is 12.276, so plot that as best as you can as well. Now the vertex, we're going to use our graphing calculator for that. So second trace, this is a maximum graph. Now if it was a minimum graph, meaning it was a upward facing parabola, I would have used minimum. But since it's downward facing, I'm going to use number 4. So again, move your cursor until you're left or right. In left bound, you have to move where you're on the left side of that axis of symmetry. Press enter. Move to the right of it. So you're going to have to keep moving that right cursor until you get to the clear right side of that x-intercept, or that, sorry, the vertex. Press enter, and for you guys, you're going to have to press enter again. So I have that the vertex is 6.125 and 185.52 if I'm rounding to the nearest hundredth, and 6.13. Okay, so there's my vertex. Now I can actually plot that. So 6.13, 185.52, and now I can connect those 3 points that I just drew. Again, I don't have to go below the x-axis or to the left of that y-axis because time can't be negative and height can't be negative. So I kind of stop my graph there. So that's going to be important for my height because you're going to say domain is t such that t is going to be greater than or equal to 0 because the lowest height is, or the lowest time is 0, up to the greatest time that we have is our x-intercept of 12.276, and we can even say the t-intercept to be a little bit more accurate. And then here we can say the h-intercept for instead of y-intercept. So using those letters is really showing that you understand that that letters can change, right? It doesn't have to be x and y, it can be any letter. So as long as you know which one actually refers to your x and which one's your y. Your range, we would say h such that h is in between 0, because that's the lowest height is when it actually hits the ground, this object being fired, up to the highest height we have is from the vertex of 185.52, and then here we still have to have that TER, and over here we'll have that HER for it to be fully correct. And that is example 5. Example number 6, what I want you to do is we're going to have a little bit of extra work here because they're not giving us the equation. They're not giving us enough information here. So we have to read the situation and come up with a formula in standard form that works with this situation. So at a children's music festival, the organizers are roping off a rectangular area of stroller parking. There is 160 meters of rope available to create the perimeter. So perimeter of a rectangle is equal to 2 times the length plus 2 times the width. So we kind of need to know that. Anytime they refer to perimeter, use that information. They're also giving us the perimeter, which is 160. So we know that 2L plus 2W is 160. What they want is they want an equation for area though. Area of a rectangle is length times width. Now, the reason they give us all this information is because we have 3 unknowns. 3 unknowns. Normally when we have quadratics, we only have 2 unknowns, which is x and y, because those are coordinates. We cannot have 3 unknowns. So that's why they gave us this. We're going to have to solve for one of the variables and actually substitute that into our equation. So we're going to start by dividing all of this by 2 to simplify this. So since they all have a factor of 2, I'm going to get 80 equals L plus W, because those guys cross each other off. So this helps us simplify the equation. Next, I'm going to subtract L on both sides. The reason being, I'm trying to isolate for one of the variables, and it doesn't matter which one you do. I just chose to isolate for W. The next step is you're going to substitute that W value, 80 minus L, into the area equation. So area is actually equal to length times, instead of W, we're going to write 80 minus L. And lastly, we're going to distribute that L. So area is equal to 80L minus L squared. Now in standard form, we always like the highest power first. So we're going to write minus L squared plus 80L. This is standard form. So remember, A is area, and that's going to represent your y value. And length, which is L, is replacing your x value. So what we're going to do is go to our graphing calculator. But what's important to notice is that there's a constant of 0, meaning that there is a 0 added here. So we know that whatever happens, the graph is actually going to start from the ground, 0. So what I'm going to do next is I'm going to put this into my graphing calculator and figure out some of those key features, like the vertex, of course, the domain range, sketch it, all that's going to be useful. So what we always want to find from the graphing calculator is our vertex, our x-intercepts, and our y-intercept is already given because we're looking at the equation, but from there you can answer all the questions. So in our graphing calculator, you're going to clear whatever's in y equals, and you're going to write minus x squared plus 80x. So instead of this L letter, we are using x's because we don't have L's to use. Now, in our standard window, we're going to keep it like this for now. I'm just going to graph it just to show you that this is not high enough. The values aren't big enough for your x and y because, one, we know the graph is starting at 0, 0 because our constant was 0, but we don't see where it ends off. Again, we don't see where the x-axis or our x-intercept is, and we don't see that vertex. So we're going to need to go higher. So instead of going to 15, let's go to 50 just to see what happens. Well, you see how we still don't see it? That means we have to go higher. So I'm going to go up to 100. So I kind of increase it gradually, and then if I have to, I increase it a lot if I'm still having trouble with it, but for me, 100 works, okay? The next thing I want is I want to change the window so I can see that vertex. So 200 is not enough, so that means let's go up to 1,000 just to see. Is that enough? No, it's not. So let's double that. So what I do is I start doubling the value until I get to the vertex that I need, and in this case it works because 2,000 is enough to see your maximum height. Okay, so it's not always going to be a maximum graph, but usually real life scenarios do end up like this. So let's go to second trace. Again, it's a maximum, so number 4. You're going to move your cursor to the left side of that vertex, so anywhere along here, press enter. Oops. Let's do that again. Second trace. I want to go to number 4. So move your cursor left bound, press enter, move your cursor anywhere to the right, which would be anywhere here, press enter, and then enter again for you guys. You should see that the maximum value is 40 and 1600. So make sure you're practicing all my graphing calculator steps in your graphing calculator. You want to be very familiar after this course with your graphing calculator and how to use it. So 40 and 1600. So what that means is when the length is 40, and we're talking about meters, it will produce a max, in this case area, of 1600 meters squared. So that's going to be that rectangular stroller parking that's created as the maximum area that you can create with 40 meters as your length. So before we continue, so we already know the graph is starting at 0. We know that it's going to go to a maximum of 1600 at 40, but we need to find out where it's going to land, which is your, or where it's going to end off. In this case, it's not something falling. We just want to know when the area is equal to 0, so the x-intercept. So let's find that. So if you guys look back at your graph, we already know that the graph is going to have an x-intercept of 0, 0 because the y-intercept is 0. So then you're going to go to second trace. You're going to go to number 2 for your zeros or your x-intercepts. You're going to move your cursor as close as you can to this x-intercept. Now, if you're moving to the left, you'll notice that your y value is positive. So anywhere y is positive, press enter. For the right bound, watch your y coordinate. The second it becomes negative, anywhere that it's negative, you can press enter for the right bound. And then for you guys, press enter again. You should find that your 0 is at 80 and 0. So that's going to be helpful for my graph. So I know that there's an x-intercept of 80. So what I'll do is I will go up by, let's see. I'm going to go up by 20, 40, 60, 80, just to fit everything in. This is going to be my L in this case, and this is going to be my A for it to make sense. And then over here for my my y values, in this case area, let's go up by 500 just to fit everything. 500, 1000, 1500, 2000. There you go. So we know that the graph is touching 0, 0. We know that it's going to land at 80, so I'm going to put another coordinate right here. And at 40 and 1600, approximately there, we know it's going to have a maximum height. So we're going to use those to draw our parabola shape. So that's our sketch. Perfect. So that's what you need. The domain, we're going to say, domain is L such that L is greater than or equal to 0, but less than and equal to 80. LER. And our range, we're going to say area such that area is greater than or equal to 0, but less than and equal to 1600 AER. Okay, so that would be the proper domain and range. Assumptions. Well, whenever we're making something or using math, it might not work for the real world because we want to make sure that we have the area to make this stroller parking. So our assumptions are that we have the space to be able to do this. The space is available because we can adjust this however we want, but if we take it and we don't have those kind of dimensions available, then we can't really do it. So those are kind of assumptions that we're making, is that we have the spaces available, that we could expand and make the length however we want it, but that might not always work. So what I'll get you guys to do is I'll give you more instruction about the exit test, so just wait on that. I hope you guys are having a good day. I miss your faces, and I look forward to hearing from you guys. Have a good day.